So we return to the differential equation that governs the motion of mass on a spring, a low amplitude pendulum, anything subject, any mass subject to a linear restoring force. Okay, there's our general equation. To find a solution, now knowing that sine and cosine functions of t would be solutions, we take a general sine function of t, sine of ct, sine of a multiple of t, and we plug it back into the equation. And by very straightforward operations, the second derivative of sine of ct being negative c squared sine ct, we get the relation, and then dividing by the sine of ct, we find that c squared equals k over m, so that c is the square root of k over m, so that x of t equals the sine of the square root of k over m. T is a solution, not the only possible solution, but it's a solution to this equation. We could have used a cosine function here, and we would have also gotten a solution. We'd have had a cosine square root of k over m t had we done that. Now, without going into a lot of detail, and I might go into detail in an extension, the general solution of the equation you see here is a combination of sine and cosine functions. It's in fact what we call a linear combination. If you've had linear algebra, you know what that means. A multiple of a sine function plus a multiple of a cosine function. A and B being the numbers by which we multiply the sine and the cosine function. Omega is just the square root of k over m, so I've just abbreviated the square root of k over m, represented it as omega. And of course there's a method behind the madness of that substitution, because we're going to get very quickly into our familiar definition of omega. Okay? Now, there are alternate forms of this. By trigonometric identities, we can express x of t as some constant c times the sine of omega t plus some theta naught. Okay? There's an interpretation of that. We're not going to talk too much about that interpretation. We didn't talk too much about that interpretation in class. We're probably going to do an extension that does talk about that. Okay, so C is just related to the relative magnitudes of A and B, and also to an extent to omega. And theta naught, same thing. It depends on A, B, and omega. But we're just talking about typical high school level rules for combining trigonometric functions. And we could also combine it into a c cosine of omega t plus theta naught. C would be different if we're using a cosine, so these c's would not be the same, and these theta naughts would not be the same. The theta naughts would be differ by 90 degrees, because that's what the sine and cosine differ by, 90 degrees or pi over 2 radians. Not important for the rest of the class today to know that, but when I do the class extension, it might well become important. Okay, so what's our interpretation of omega? Well, we very recently talked about the motion of a reference point around a circle with angular velocity omega. And this is characterized by theta as a function of t being equal to omega t, and the x projection of the point on the reference circle having radius r, is a vector x of t. So the projection of the r vector, if you wish, is the x of t vector. And in this case, x of t is just the r times the cosine of theta, which is r times the cosine of omega t, since theta equals omega t. So we got x of t equals r cosine of omega t. Now, does that remind you of anything we've seen up here? Well, it certainly should. Right there, we have something that is of the same form as this. We have c cosine of the quantity omega t plus theta naught, and this is the same. This is an instance of this, where theta naught is 0 and c is equal to r. So this is an equation of motion for some linear, mass subject to a linear restoring force, where omega equals the force constant divided by its mass, and r is, it turns out, the amplitude of the motion, because of course the maximum x of t would be equal to r at this point or this point. The magnitude of x of t would be r at this point of the circle or at this point of the circle, corresponding to the maximum displacement of the oscillator from its equilibrium position. Okay, so x of t is r times the cosine of omega t, and we can represent that then as the x component of motion of a point around the reference circle, where the point starts at theta naught equals 0 and moves with angular velocity omega. Okay, so, and I just comment here that this x of t is of this form with theta naught equals 0 and c equal to r. And that is a position function for simple harmonic motion.